So my review video is going to concern orthogonal trajectories. And to discuss this, we first need to discuss what orthogonal means. Orthogonal basically just means perpendicular. So if we have two families of functions, f1 and f2, we can say they're orthogonal if any function in family f1 is perpendicular to any function in the family f2. Just to make this really simple, using familiar equations, I'm just going to read you an example from our lecture. So the first family, y equals mx, the differential equation with respect to x, dy dx equals m. This is very easy to work with. So here we can find that m equals y over x and plug that in. dy dx equals y over x. So that's the differential equation for the first family. Now for the second family, we need to find one that would be orthogonal. Since this is the slope, when we work the line, we know that the slope is a negative reciprocal if they're perpendicular. So the differential equation for this would be dy dx equals negative x over y. Okay, now to find the solution, we're going to need to integrate, and we're going to do this by using separation of variables. So y dy equals negative x dx. Integrating both sides with respect to x, we get y squared over 2 equals negative x squared over 2 plus c. And bringing them to the same side and multiplying by c1, we're going to get y squared plus x squared equals c, where c equals 2c1. Now that's a pretty basic example. I'm going to go on to do an example from the end of the lecture where there's a bunch of example problems. Oh, this is falling. Okay. Now this will be example 3. Y equals c minus x to the third over 3 minus x. Differential equation with respect to x would be dy dx. Derivative of c is 0. Derivative of negative x to the third over 3 is negative x squared. Derivative of negative x is negative 1. Okay, now for the second family, we want something that is orthogonal to it. So dy dx equals negative 1 over negative x squared minus 1. Or dy dx equals 1 over x squared plus 1. Using the separation of variables, we get dy equals dx over x squared plus 1. Integrating both sides with respect to x, y equals arctangent of x plus c. And now I'm going to go over to the trench book. And I'm going to do a trench 4.5, and I believe this is number 27. So the problem is y equals c e to the 2x. So that's our first family. Now the differential equation for this family with respect to x, dy dx, integrating this, we bring the 2 down, 2c e to the 2x. So that's for the first family. I'll label as f1. Okay, now to find f2, we're going to take the negative reciprocal of this. Now to make this easier to work with, we want to transform c, and we come up here, we find that c equals y divided by e to the 2x, or c equals y e to the negative 2x. And we'll put that in right here. So dy dx equals 2y e to the negative 2x times e to the 2x. And we see that if we combine those, we get e to the 0, which means that here dy dx equals 2y times 1. Okay, so now we're going to find the differential equation that would be orthogonal to that. So dy dx equals negative 1 over 2y. Now we're going to integrate, and do this, we're going to do separation of variables. So 2y dy equals negative dx. Integrate both sides with respect to x. Y squared equals negative x plus c. So that's pretty easy. And if we want to put this in a way that might look a little nicer, we can do y equals c minus y squared. Or if you need to put this in a calculator and get it in terms of y, we can do y equals plus or minus radical c minus x. Okay, and I'm going to go back to the lecture and do one more example from there. And also, before I move on, this is how it would look if we put it into the GraphEQ program. Because that's harder to visualize. You know, with the first one, we get a solution that's a series of lines through the origin, and we get a series of circles. It's pretty easy to see that that's perpendicular. But it's a little harder with problems like this. But you could see at each point where they cross, it's roughly perpendicular. And that's a good check. So finally, returning to the lecture, I'm going to do problem 4. So y equals negative tangent of x over 2 plus c. My pen's running a little bit. Okay, so for F1, differential equation dy dx equals negative 1/2 secant squared of x over 2. Okay, and if we want to take, if we want to find F2, dy dx for that equals 2 times cosine squared of x over 2. And we can do that because 1 over secant is cosine, because secant is 1 over cosine. Okay. Now, separating the variables, dy equals 2 cosine squared x over 2 dx. And using a trig substitution, we find that dy equals cosine of x plus 1, which I just simplified pretty quickly. So we're going to integrate both sides and find that y equals sine of x plus c, and we find that that is the function 2 that is orthogonal to the original.